Hi, my name is Ben. I'm a technology evangelist in Aerospike. I have around 17 years of experience in the industry. I started my career as a software developer. I've been using relational databases at the beginning of my career until around 2009, 2010, that I was introduced to the world of Hadoop and distributed computing. I started using HBase back then. And then around 2012, 2013, I started to use MongoDB. I was a MongoDB developer for a number of years. After that, I was introduced to Cassandra. I used Cassandra for a number of years, and then I joined the company that is the main contributor to the Apache Cassandra project, DataStax. I was there for 3.5 years, and now it's 2 years that I'm working in Aerospike. So the title of this talk is Faster, Cheaper, and Greener Big Data. So without any further ado, I want to dig into the talk and give you my point of view about the state of big data. You possibly saw something like this before. There are things in the world that are considered to be fast, there are things that are good, and there are things that are considered to be cheap. And the intersection of these things, usually fast and good things, are very expensive. The good and cheap things are usually very slow, and the fast and cheap is chocolate ice cream. That triangle in the middle is kind of a unicorn, right? So some people believe that unicorns don't exist, but I'm one of those people that look at hippos and say that yeah, they are actually by definition unicorns. So I don't necessarily agree with this, but the sentiment that you should focus on that triangle in the middle, I think that's a good thing to have. If you are a technologist, if you have a business, you have to always focus on finding technologies and services that are fast, good, and cheap. But finding things that are inside that triangle is a little bit difficult, because the definition of fast and the definition of good and the definition of cheap is changing throughout time. So when you're looking at that triangle, you also have to consider what is the definition of these things throughout time. So let me give you a few examples. So if you are in 1990, in terms of computers, something that is capable of responding back in order of a few seconds is considered to be fast. And something that is capable, something that can do some specific functionalities, is considered to be good. So if you look at that time, Oracle, or in general, relational databases are right in the middle of that triangle, right? So they are intersection of fast and good and cheap. And the reason that I'm saying that Oracle is cheap is that, back in the day, the size of the disk was very limited, and disk was very, very expensive. Relational model in general tried to reduce the amount of data on disk. So they were trying to optimize for the thing that was really expensive. So Oracle ended up to be cheap, fast, and good. But as the time moves on, Oracle has started to move out of that triangle, right? Firstly, disk has started to become cheaper and cheaper. So that thing that Oracle was optimized on wasn't necessarily the most important thing. So it started to move away from cheap. And then the definition of fast has started to change, right? Something that was second was considered really, really slow. Of course, Oracle, when the CPUs were getting faster, Oracle was getting faster as well. But, there was a limit to that. When it got to, you wanted to have the scale of internet, Oracle wasn't fast enough. So Oracle was in that triangle, but slowly moved outside of that triangle as the time moved on. If you go towards around 2010, you can see that the definition of fast was around hundreds of milliseconds, and the definition of good was now scale up. We wanted something that instead of running it on one machine, we can run it on multiple machines. And at that time, HBase was in that space. It was fast, it was a scale out, and it was cheap because you didn't need to buy a very expensive machine to run your system on. You could basically buy some commodity hardware and run the system on the commodity hardware. But again, if you move 5 years forward, the definition of fast changed from hundreds of milliseconds to tens of milliseconds, and HBase couldn't do that. So it started to move outside of being fast. And we started to feel that okay, a scale out is not necessarily the thing that we need. We need a scalable. We want something that we can add things to it instead of having just like 50 servers. So HBase has started to move out of that triangle. Exclamation point is that HBase is actually scalable, but if you ever done it, you would agree with me that it is not. It's, if you build it with 10 servers, it works. If you want to make it 11 servers after 10, it's going to be ridiculously difficult. So it moved out of that. Another example of that is 2010 definitions are tens of milliseconds. The definition of good is now modern. We've been dealing with this relational model for 40 years, 50 years by 2012. And at the time, object-oriented programming was the main type of programs that we were using. And we didn't really like this mapping that we constantly needed to do from objects to tables. So something more friendly, like a key value data store or a document store, was more suitable for developers. At that time, again, MongoDB was right in that middle place. It was fast, it was modern, and it was cheap because in comparison to the other technologies that were in the market at the time, it was considered to be significantly cheaper. But again, moving forward, it wasn't fast anymore, and it wasn't cheap, mainly because of the competition in the market from the other databases that were also modern and fast. Last example, I promise. 2015, again, fast was milliseconds, good was scalable, and we had cheap, and Cassandra was there. It was very, very fast, and it was scalable. It worked on commodity hardware of the time, and it was considered to be really, really good. But again, moving forward, it moved out of that good position first, because it was very difficult to operate, and it wasn't considered to be cheap anymore because it wasn't efficient. Right? It wasn't using hardware very efficiently. You had to throw a lot of hardware to it. So it slowly moved out of that class. So now let me talk a little bit about Aerospike. The first release of Aerospike came out around 2010. At the beginning, it was designed to solve a very, very specific problem for the ad tech industry. If you don't know anything about the ad tech industry, think about it like this. The scale that they need to handle is the scale of Amazon, Facebook, Google, Candy Crush, all of them combined. You know, when you go to a website like Amazon, you always see some advertisement on the side of the page. All of these ad tech companies are constantly trying to place an ad in those things. So the throughput that they need to handle is massive, and they need to be fast. And they are fast. You possibly saw this, that you go to a website and the ad is loaded faster than the actual content that you are there to see. So they wanted to be able to handle this massive throughput with a very, very low latency. And around 2010, the only way that you could do this low latency was with in-memory caches. So you had to put all of this on cache. But in 2010, there were two problems with cache. One of them was that RAM was very, very expensive, which is still today, but significantly cheaper than back in the day. The second thing was that you couldn't have as much as RAM as you wanted in a single machine. Right? The limit of very, very good server, the physical limit that you had on a single machine was around 64 gigabytes. You couldn't have more than 64 gigabytes of RAM on a single machine. So Aerospike came in to address that problem, said that, okay, we can solve that problem by, instead of putting it on RAM, we are going to create an index on RAM, and we are going to put the data on SSD, and we are going to provide you with the same type of throughput and latency that in-memory databases provide, but we are going to do that with SSD. So at the time, that definition of fast with tens of milliseconds, Aerospike was capable of doing less than a millisecond latency by storing the data on SSD drives. So I put it in fast, not cheap and good, but I have to explain it why. So I said that it was cheaper than the solution that was available to ad tech that was putting all of things in memory, because SSDs were significantly cheaper than RAM. But SSD was a very expensive hardware, right? If you wanted to put things on SSD, you really needed to have that kind of use case. If you didn't have that use case, it ended up to be relatively expensive. And it wasn't good because although it was, a scale out and a scalable and modern key value database, but it wasn't really capable. It missed some of the features that you expect to have from relatively general purpose databases. But moving forward in few years, when now the definition of fast was milliseconds, Aerospike was still, less than a millisecond. So it still was fast. Instead of moving out, it was still staying in that fast category. But during these 7 years, a lot of features that general purpose databases required were added to the database. So now it suddenly had secondary indices. It had multi-region data center replication. It had strong consistency. And then on top of those things that made the database capable, it started to have other things that made the database operable. Being operable with Apache Spark, being operable with Apache Kafka, or being able to work with Kubernetes and things like that. So these things were added in the years to come, and it made the database moving from just being fast to being fast and good. But it's still in 2017, SSDs are relatively expensive. Moving forward to 2023, the definition of fastest sub-millisecond, Aerospike is still, it's 13 years that Aerospike is capable of doing sub-millisecond. So it is still considered to be fast. It is good because, well, it is still operable and everything, but now it is efficient as well. Efficient, it means that it doesn't need that much resources, so it can reduce your costs. So it played with the cheap as well. But it's also cheap because for the first time in 2022, the cost of 1 terabyte SSD became lower than cost of 1 terabyte spinning disk in 2010. Right, so the SSDs were constantly getting cheaper. Of course, spinning disks are getting cheaper as well, but now SSDs are not more expensive than 1 terabyte of a spinning disk used to be in 2010. So the database is now cheap. And SSD might sound an advanced technology, but you have it on everything. You have it on your phone, you have it on your laptop, it's everywhere. I hardly see anywhere any spinning disk. So throughout the time, instead of moving out, Aerospike is slowly moved into that triangle. So I don't have a crystal ball, but if I want to guess that what's going to be important in the future, I think that fast is still going to remain sub-millisecond, because to be perfectly honest, I don't see how you can make something faster than what Aerospike is doing right now. But the definition of good going to become green. You can hear it everywhere. All of the sea levels of 66% of the FTSE 100 have agenda for reducing their carbon emissions. So I'm assuming that good is going to become green in the next 7 years. So if we go back to this picture again and say that, okay, we had fast, cheap, and good, and I said that okay, in the future, green is going to be some kind of definition of the good. And by the way, when I'm saying green, I don't mean that capable and operable and those things are not important. It's including all of those, but the thing that is going to become important is green. So if we assume that we want fast, cheap, and green, something interesting is going to happen. If you look at this diagram very closely and try to squint your eyes a little bit, you can see that actually these three things are very, very similar to each other. Let me explain you why. When you have one CPU, the CPU can do a number of operations per second. A 2.4 gigahertz CPU can do 2.4 billion operations per second. So imagine that this CPU that I have here can do 50 operations per second. If I have an algorithm that takes 10 operations to complete, it means two things. First one is that it's going to take 1/5 of a second to complete, or 200 milliseconds. The second thing it means is that I can run 5 of these tasks in 1 second. If I own a business that needs to run 25 of these tasks, the thing that businesses were doing in the past was that they were adding more resources to be able to do those 25 tasks. That's the thing that we are used to do. But there's another way to do that as well. If somehow I can make that algorithm that I have, instead of running on 10 operations, running on 2 operations, then I have again two things. First thing is that this operation now is going to take 1/25 of a second, or 14 milliseconds, 5 times faster, but I can run now 25 tasks in 1 second on one CPU. So basically, by making the things more efficient, I reduce the number of resources that I require to do the same thing that I wanted to do for my business. So by looking at that, I can say that okay, fast and cheap are kind of the same thing, because when you make something run faster by using better algorithms and data structures, you're using fewer resources, and resources have a cost. If you can reduce your resources, you're going to become cheaper. But you know what else is cheap? Talk is cheap. I can show you something here. So this is a test that I have, and if you want, I can show you this test whenever you want. So first thing, this application that I have every second is printing a line showing that what it did in the past second. So if you look at this side of the log that is being printed out, this program has been running for an hour, right? So I've been running it for an hour. So I'm not showing you something that is just like, I ran it for the past 5 seconds and I'm showing you just a snapshot. If you look at here, the number of items that has been processed, so basically the number of the data points that are in the database is around 1 billion objects. And if you look at this, the number of writes that I'm doing per second is around 169,000 operations per second. Number of updates is around 31,000 operations per second. So basically something around 200,000 write operations in total. And then I'm doing around 400,000 read per second on the database. In total, I'm doing 600,000 operations per second. But that's not necessarily saying fast, right? If you throw hardware at something, you should be able to do that, right? So let's not get excited yet. Let's move to the next slide. So the next slide shows that this is for half an hour. Again, I'm not showing you something for like 5 seconds. This is half an hour. The throughput that I had for the past half an hour is something like a flat line, 200,000 writes per second. And the number of reads is, again, like a flat line, 400,000 operations per second. And you might say that, oh, okay, what are these fluctuations? Well, I'm running this on the cloud. I don't know, you might have noisy neighbors. I don't know, there might be network problems. I don't know, there might be a lot of things happening, but it is almost flat, right? And now this is the latency during that exact same half an hour. If you look at the timestamps, they are all of them around the same time. So exactly around the same time that I was doing 400,000 operations per second, during half an hour, there were 10 operations in total that were slower than 2 milliseconds. Right? 100% of my operations were faster than 2 milliseconds, right? But 99.999999% of them were faster than 1 millisecond. And then for my writes, it's also the same. With my writes, again, 99.9% are running faster than 1 millisecond. And I do have a few, if you color match this one, I would say that there are around 50 operations that are taking longer than 1 millisecond, but it's still, everything is lower than 8 milliseconds. So when I'm talking about, fast, I mean this fast. I don't mean just like, ooh, we are fast. It's very, very fast. It's cache-like a speed, fast. And then all of this was running on 4 nodes. Just 4 nodes. I was showing you this demo on 4 nodes. And if you want, I can launch this demo and show it to you in person whenever you want. And I'm running this on these machines that are i4, i4x large. The reason that I chose these i4, i4x large machines is that they are reasonably the same order of magnitude as my laptop. My laptop has also 16 virtual CPU cores. I have 64 gigabytes of RAM, so this machine has double the size of the RAM. And I have 4 terabytes of disk. These machines have 3.7, right? So on 4 laptop-sized machines, I'm running the throughput that you saw. And by the way, if you're asking this one, this is the machine that I was running my test from. So anyway, I have 4 machines, I have replication factor of 2. So if you lose one of the nodes, the data is still going to remain available. This cluster that I have is around 3 terabytes of unique data capacity, and I can drive 600,000 operations per second on it. How much does it cost? The hardware on AWS costs something between $31,000 to $36,000, depending on where you deploy the system. And this is without AWS discount. This is just reserve cost on AWS on different things. If you compare this price with how much does it cost to run such a system, such throughput on something like Dynamo in one region, it's going to cost $2 million. Right? I'm not joking. You can go to AWS pricing calculator and put these numbers in, 600,000 operations, 200,000 writes, 400,000 read, for 3 terabytes of data, reserved price on Dynamo, it's going to be $2 million per year, more than $2 million per year. So when I'm talking about fast means cheap, that's my proof for that. So, okay, to prove that fast means cheap. Now, what about green? So last year, I wrote this paper that was published in IEEE. It's talking about software efficiency and its relation to CO2. So if you're interested, you can scan the QR code. It's going to take you to the article that I posted. It's titled there. It's an executive summary of the paper that I wrote. If you're interested, you can read that. But if I want to give you a high-level overview about what I've done, I'm saying that if you pick a workload and a technology, you can come up with a resource estimation. What it means is that imagine you have 10 terabytes of data and you want to store it in a database. So 10 terabytes is my workload. And now I can pick a technology. The technology can be Aerospike or Cassandra. So if I pick Cassandra and 10 terabytes of data, I can come up with a resource estimation I can do the same thing with Aerospike and 10 terabytes of data and come up with a different resource estimation. When I have the resource estimation, I can calculate the emissions that manufacturing those resources produce, and also the energy usage emission of those resources. And if I put them together, it's going to give me my platform emissions. So you might say that, but is it important? Who am I to tell you it is important? I can just give you the numbers. So for 1 petabyte of data, storing 1 petabyte of data in Aerospike, the amount of platform emissions is around 110 tons of CO2 emissions per year. If you go with Cassandra, it's going to be around 600 tons, right? Something around 500 ton more CO2 emission per year, which is equivalent to the amount of CO2 emissions that 50 hectares of tree absorb during 1 year. So that's the thing that I'm talking about. But if you look at it, the amount of CO2 emissions is coming from manufacturing emission and energy usage emissions. That both of them are driven from resource size. So if I have a solution that uses fewer resources, it automatically means that you are reducing your CO2 emissions as well. So based on that, if you think about it, the same way that we say that faster means fewer resources mean cheaper. Faster, fewer resources, it also means greener. So you can see that fast, cheap, and green are basically the same thing. I want to leave you with this last sentence. In 1940, Winston Churchill said that if you are going through hell, keep going. So I think in our time, we can upgrade this sentence and say that if you are going through hell, keep going faster. Thank you very much.